Hey Fizz Kids, Mr. C here, and today we're going to talk about the relationship between forces and motion because it's pretty cool. And basically, this is just going to be my boy Newton's first and second laws. Newton might be one of my most favorite people in physics. Why? Why not? He's almost the father of physics, if you think. But what is the relationship between force and motion? Well, if we have a motion diagram, the acceleration arrow always points in the same direction as the net force on an object. Now, that's not saying it's pointing in the same direction as every force on the object. All that's saying is that it points in the same direction as the net force on the object. So that's if we took all of our forces, we added them up, what is the direction of the net force on that object? If our net force points in the same direction as our object's velocity, the object speeds up. If the net force points in the opposite direction, it slows down. And the one reason this kind of makes sense is basically force and acceleration point in the exact same direction. They're both vectors, they both go in the same direction, which means that we know that if we have positive velocity and positive acceleration, or negative velocity and negative acceleration, we're speeding up. And if we have a positive acceleration and a negative velocity, or a negative acceleration and a positive velocity, it means we're slowing down. And the same thing goes with forces. If we're in the same direction, our object speeds up. If our force and our velocity are in different directions, though, we're going to slow down. If the net force is 0, that means the object continues to do whatever it's doing with no change in velocity. If it's at rest and the net force is 0, it's going to stay at rest. Let's say it's moving and there's two forces on it, but the net force of those two forces is 0. That means it's going to keep moving at that constant velocity. So a net force of 0 just means we're moving with constant velocity. That kind of takes us to my boy Newton and his first and second laws. Well, Newton's first law is that when our net force is equal to 0, our object will either remain at rest if it's at rest, or it will maintain a constant velocity. So it'll keep moving at the speed that it was moving at to begin with. This is also called the law of inertia. You might have heard a phrase, an object at rest will stay at rest, an object in motion will stay in motion unless acted upon by an outside force. Now, if we want to change what our motion of our object is, we need a force. We need some net force, specifically acting in a direction. Newton's second law of motion is that our F net is equal to ma. And that's basically all that says is that a net force on an object produces an acceleration that is directly proportional to the force and inversely proportional to the mass. Pretty cool. And the way that it's phrased is more so like acceleration is equal to F over m. If we have a really big force, we're going to have a really big acceleration. If we have a really big mass, though, we're probably going to have a bit of a smaller acceleration. So the acceleration of our object produced by a net force is directly proportional to the force. The bigger the force, the bigger the acceleration, and inversely proportional to the mass. So the smaller the mass, the smaller the acceleration. The direction of the acceleration is in the exact same direction of the force. Make sure you remember that force and acceleration go in the exact same direction, which is pretty cool. So anytime you know the direction of one, you automatically know what the direction of the other one is. So the net force, this is a note. You only have a net force like this whenever our forces, or the sum of our forces, is unbalanced. So like, let's say, I'm pushing one way with 5 newtons. Maybe I'm exerting a force on this box this way of 5 newtons, but my friend over here is only pushing on the other way with 3 newtons. Well, the net force is actually going to point that way with the sum of 2 newtons. Pretty cool. So, how do we find the net force? Because that seems like it's going to be pretty darn important if you ask me. How do we find what the net force is? We keep talking about net force, but we haven't quite talked about how we can find it. What we do know is that the net force is the sum of all of the force vectors acting on our object. It's not some new force that's being exerted. It's just the combined effect of every force that's being exerted. So it's not something new. It's something that whenever we add up all the forces that are already there, this is what we get. find the net force, we have to first draw a free body diagram. That's very, very important. Always draw a free body diagram. If you don't have this free body diagram, you're not going to be able to properly identify all the forces that are on your object, and you're going to miss one, or maybe you'll get the direction wrong. So always draw a free body diagram. You're going to want to write an equation by adding or subtracting each of the horizontal forces in your diagram. If the force points to the right, it's positive. If it points to the left, it's negative. So let's say, our force body diagram looks like this, where it's F1 and F2. Our F net is equal to the sum of the forces, which would be F1 plus F2. But because F1 is pointing to the left, it'll be minus F1 plus F2. So remember, if our force points to the left, it's negative, and if it points to the right, it is positive. And finally, we're going to repeat the exact same steps, but with the vertical direction. Because force is a vector and direction matters, we can only add similar vectors together. So we can only add horizontal vectors to horizontal vectors, and we can only add vertical vectors to vertical vectors. We can't add a vertical vector to a horizontal vector. It'd be like if I said, hey, what is 5 oranges plus 6 apples? Well, you don't know. You can't compare oranges and apples. It doesn't make sense. And remember, whenever we're talking in the vertical direction, up is positive and down is negative. And then once you have your net force, you either set it equal to 0 or you're going to set that equal to ma. So if we're not moving, or we're moving at constant velocity, we're going to set that equal to 0. If we're moving with some acceleration, we're unbalanced, we're going to set it equal to ma, and then we solve for whatever our problem is asking for. So example, we have this bungee jumper here, and he's just hanging from a rope. His friends left him out there hanging. I know, they're mean. Who would just leave their friend hanging like that? But we want to know what the tension in the rope is if a man is hanging at rest, has a mass of 100 kilograms. So, our first step, we want to draw out our free body diagram. So we're going to do our little dot that represents our person. And in this case, we have the force of gravity, which points down. And we have our tension force, which points, Ft, which points directly up. There's no horizontal forces in this case. There's not like a breeze coming by, or there's no one pushing him. So in this case, we only have vertical forces. The next thing that we're going to want to do is we want to write out the sum of our forces. So we know that F net is equal to the sum of the forces, which in this case is going to be our tension force plus the force of gravity. But the force of gravity points down, so we're going to go ahead and rewrite that as Ft minus Fg. And that's equal to our net force. The next thing we have to do is decide, well, we're going to set this all equal to ma, or we're going to set it equal to 0. And in this case, we're going to set it equal to 0 because we're not moving. And because we're not moving, our F net is equal to 0. So we know that 0 is equal to Ft minus Fg, or Ft is equal to Fg. We know what the formula for Fg is, so Ft is going to be equal to mg, which will be 100 kilograms times 9.8 meters per second squared, which gives us a force of tension that is equal to 980 newtons. Pretty cool. Notice I didn't put in a negative sign here for this 9.8. The negative is actually accounted for when I subtract Fg. So don't do a double negative. Otherwise, you're going to get, we get a negative tension force, and that wouldn't make sense because we know our tension force is supposed to be positive, and it's supposed to point up. Pretty cool. So another example. A car is being towed by a rope with its brakes locked. It accelerates to the right. Wow. Whoever was doing this didn't quite do it well. I mean, who the heck tries to, tow a car with the brakes locked? Anyway, if the mass of our car is 820 kilograms, what is the normal force? Well, the first thing we want to do is we want to draw a free body diagram. So in this case, well, our brakes are locked, which means we have some sort of frictional force that's opposing our motion. We're going to call it FSK, FFK, static or kinetic friction. And because we're moving to the right, friction always points directly opposite of our motion. So it's pointing to the left. We have our tension force from our rope, which is pointing to the right. Notice I draw this larger than my frictional force because the size of our arrow does represent the size of the vector. We have our normal force pointing up, and we'll have our force of gravity pointing down. So what do we want to know? We want to know what the mass of the car, of an 820 kilogram car, is. What is the normal force? Well, normal force is a vertical force in this case, which means we want to write our F net in the vertical direction. So that's equal to the sum of the forces in the y direction, I'm going to call it. And in this case, that's going to equal to Fn plus Fg. But because Fg is pointing downward, we're just going to write this as Fn minus Fg is equal to F net. Because the car is not moving up and down, right? We're not moving up and down. There's no motions. Zero motion up and down. Zero motion up or down. That means F net y is equal to 0. The F net in our vertical direction is going to be equal to 0. So we can set this all equal to 0. And we find that our force of gravity is equal to our normal force, which means our normal force is equal to mg. And Fn is going to be equal to 820 kilograms times 9.8 meters per second squared. And I'll go ahead and let you plug that into your calculator. The next thing you know is they say if our tension in the rope pulls is 300 newtons and the frictional force is 100 newtons, what is the acceleration of the car? Well, if I want to know what the acceleration of the car is, basically all I have to do is I have to write out, the car's moving in the horizontal direction, so I want my horizontal forces. So my F net, and I'm going to call this x, is going to be equal to the sum of those forces in the x direction, which is going to be equal to that frictional force plus our tension force, or in this case, it'll be the frictional force is negative because it's in the left, plus our force of tension. And because we're accelerating, that all has to be equal to mass times acceleration. We want to solve this for acceleration because that's what we want to know. We know that our acceleration is equal to our force of tension minus that force of friction, all divided by the mass, which in this case is going to be 300 minus 100, all divided by 820, which actually gives us an acceleration of 0.37 meters per second squared. Pretty cool, pretty cool. So, our last question, this is where we connect it to motion. If it starts at rest, how far will it have traveled in 10 seconds? Well, we're going to make our little diagram. We know that x0 is equal to 0. xf, we don't know. That's what we want to find out. Our initial velocity is 0. We don't know what that final velocity is. We know what our time is. It's 10 seconds. And we know what our acceleration is because we just solved for it. It's 0.37 meters per second squared. We want to identify an equation that we can use, and we're actually going to use our displacement equation. So xf is equal to xo plus v0t plus 1/2 at squared. We can go ahead and plug in values, and we find that xf is equal to 0 plus 0 plus 1/2 times our acceleration times time squared, or 1/2 times 0.37 times 10 squared. And I'll let you go ahead and plug that into your calculator, but that's going to give us what our final position is. Pretty cool. So that's kind of how motion and force works. We can actually use our forces and our net force to figure out what the acceleration of our object is. And once we know that acceleration, we can then start solving for things like if we could find out time, how long it took to go a certain distance, or in this time, how far to go, what its final speed is, or all this other cool stuff. The last sort of note on motion is we've seen two different ways to define acceleration. We have that operational definition. So basically, what is acceleration? And according to that definition, acceleration is equal to our change in velocity divided by our change in time, because that's physically what it is. There's also the cause and effect definition, though, and that's basically saying that the acceleration is the effect of some force acting on a mass. And depending on the type of problem that you're going to want to solve, it's going to depend on how you want to define, your acceleration. If you have information about like velocity and times, yeah, we're going to want to use the operational definition. However, if we have more of what caused the motion, so we have forces, and we're saying this force, this tension is causing the motion, we're going to want to use the cause and effect definition to solve for what our acceleration is. After watching this video, go ahead and answer video check 2 in the Google Forms, and I will see you in class tomorrow, I guess, and we'll talk more about forces and motion and do some practice problems.